Okay, I believe we are live. We're here with Joel, or SFBMOD, as he is called so far.
Hello.
You're going to change your name someday, right?
Maybe. Let's see.
Oh, shit. Yep. I got to shut this. Hang on a second. Damn it. Okay. Got it off. Okay. Let's see. I got to get my shit together here. Anyway, so we kind of briefly, did I talk to you the other day?
You asking me?
Yeah. Have we ever been online together?
We spoke briefly one night on Tangelo's channel, I believe.
Okay, we did. Okay.
We talked about selling a box of periods, which we thought was hilarious.
Oh, yeah. Okay. To Neff. He definitely needs periods. The man cannot finish a sentence. He repeats himself. Anyway, let's see. So we disagree very much on a whole bunch of things. So this should be interesting. Yeah. But we are. I think we're both programmers. So you're a programmer?
Yeah, I heard about that. I heard you're a software engineer. Yes, sir.
Yep. So, I work on Ruby on Rails and JavaScript, React. Have you ever done either of those? Or
very briefly? That sounds like you're a front end guy. My last position, I was doing a full stack. I was doing .NET Core with Angular 10, Postgres, SQL, and things like that. I'm more of a full stack developer.
Yeah, I'm a full stack developer too. Rails is back end, and well, you can do front end out of it, but we usually do front end using React, JavaScript, ES6 with Rails, and then sometimes use Node on the back end, or I don't know what else I've used. I've never used Django or Python. Okay.
That was one of my first professional jobs was with Python and Django back in California.
Yeah, I've never used that. The last contract I had, they were using it there for doing some data science and stuff. We had some big data we were dealing with. Yep. But anyway, yeah, I've been programming for quite a few years. Too many.
Yeah, I'm sure we can have fun just talking about that alone for
about 40. 40 anyway. 40.
Nice.
Yeah. And I got into microcomputers back when you had to toggle the operating system into your computer with a front panel.
Nice. So you're an old guy, in other words, right? You used to age
69.
Dang, I thought I was old.
Yeah.
I'll be 46 next month, right?
Oh God, you're ancient. You got one foot in the grave.
Yeah. I thought you said I'm a young whippersnapper.
Yeah. Well, I can call you a kid, but I got in on the ground floor of microcomputers through hardware. I was doing hardware at the time, and working with microprocessors, microcontrollers, and doing a lot of test jigs for customer service and a computer store, and that's where I started out. But we quickly got into software, and that's kind of where I stayed. And then I kind of came up through the early 80s when everything was exciting.
Cool. Yeah, I've done point of sale contract work. When I used to work for Texas Instruments, and I did all of the PLC SCADA network stuff. So there's probably some similarities there too.
Anyway, somebody asked me if I did punch cards. No.
That's a little before our day, hopefully, right?
Yeah, well, I learned how to program BASIC on a computer at a college when I was in college.
What kind?
It was a Wang 2200 with 4K of. It had that wire core RAM, with the magnets. Yeah,
it's pretty cool. Memory or whatever.
Yeah, it was pretty interesting. But we had 4K of RAM, and it had a cassette, so you could download your program. And my calculus teacher got me into. He brought me over to the computer lab and basically sat me down and turned the computer on and suggested. And I said, no, I'm not interested. I was interested in audio at the time. Like I was going to school for electrical engineering, so I was interested in audio. And I never thought computers would be something that interested me. But anyway, 80 hours later, I staggered out of there knowing BASIC. So that was the beginning of it. So it's pretty cool.
You reminded me of the IBM CEO, how he once said that the computer would never catch on to the public.
Yeah, exactly. Yeah, I was like, well, I thought it would catch on, but I didn't think it was for me. I didn't think it was interesting. Right. And, I had no idea how interesting it was going to be.
So yeah, I had a similar, I guess, start. I was 8 years old sometime in the 80s. My dad brought home a Timex Sinclair 1000. I don't remember how much RAM it had.
Yep, I remember those.
Yeah, it was black and white, had a tape cassette.
Yeah.
I taught myself basic on that when I was a kid. I tried to, I ported, I made the worst game ever made, which is E.T. on Atari 2600. I made it even worse. I ported that Timex. It was, it's not something to be proud of.
Yeah, my sons got their start by sitting on my lap and pounding on the keyboard. Nice. And then they own their own consulting company today. So both computer guys. Yep. So one of the things that you talked about the other day, well, there were a lot of things you talked about. Okay, I asked you if you were a young Earth creationist, and you give me this whole runaround about time being relative. But you know that you showed up at 5 o'clock, and I showed up at 5 o'clock, so time isn't all that relative between us.
Well,
so the difference between 6,000 years and 4.2 billion years, you got to admit that's significant, right?
Well, sure, but did you get to hear that later on in that same conversation the other night, where we talked about the premise for the 4 billion year old age of the Earth, based on the meteorite assumptions?
Oh yeah. That's a discussion I want you to have with Leo Filius on this channel.
Sure.
I don't want to do physics or cosmology or radiometric dating or any of that. I am a genetics guy and Pop 10 and stuff like that.
Okay.
So it's kind of, but I mean, at least, let's try to establish how old do you think the Earth is? How old do you think the Earth is?
I have, it's not only that I don't know, I don't think anybody can really know. And so there's all kinds of assumptions one way or the other. Like I said, as far as science and physics is concerned, the universe can be recreating itself every 6 seconds. As far as, all the debates a century ago from Einstein and Planck and Heisenberg and all those guys, it's really, the question is, it's going to always be out there. And then when you really go into the deep quantum mechanics of reality, it just becomes basically irrelevant, which is what I think you're also kind of criticizing for saying. So because, and I saw one of the comments from a person named Laura on your channel saying how, you forgot to mention the speed of light. So all of that is variable. None of that is static. The assumptions are grew up in school and public education. All those things they're not scientific. So it's not that we don't know. It's that based on where we are right now, there's so much variability. I mean, there's things like Einstein crosses. There's all kinds of time dilation effects. I've talked about this ad nauseum in great length. We need to get at least probably a dozen or more parsecs, if not a full megaparsec, outside of our current local space, just to be able to erode some of the presumptions we have on how time is passing locally.
Okay, you told me you're how old? 46?
Yeah.
So based on that, how old do you think the Earth is?
No idea.
Oh my God. Okay.
Science requires observable, repeatable, empirical evidence. So the only thing for the 6,000-year-old claim to base that on is the genealogy in the Bible. The only thing to base for the 4 billion-year-old claim is the uranium to lead decay rate of meteorites. Both are assumptions. Okay. So I don't like to rely on assumptions. I'll wait for evidence. And if anybody's got some good clues on what better to test that with, other than those two premises, I'd love to learn about it.
So then you would concede that time isn't something that falsifies something like evolution. If it's relative, it could be 4.2, it could be 6,000.
Yeah, or 6 seconds, right? And it's not that it falsifies it. The problems I have with evolution is that, again, the scientific method, as Christians like Bacon started it requires empirical, repeatable, observable evidence in real time. So if we can't do that, we can't repeat evolution, then it's just like most people concede, it's just a theory. We don't have scientific evidence for it yet. And that's what this whole conversation is about. What evidence do we have, and then what do we compare it with?
Okay, you believe that we have evidence for how chemistry works, right? Like how sodium.
Absolutely.
Yeah, okay.
Yeah, that was my first undergrad.
And you believe molecular biology, right?
Well, see, that's silly, of course.
Okay, good.
The problem is how does things like that happen theoretically on its own versus being designed?
Well, what happens on its own. I mean, you don't believe that there's supernatural intervention in you when you grew from a zygote into what you are now, right?
Well, the origin certainly could be supernatural, as people like Jastrow to Planck talk about, and Einstein.
Well, okay, so you're talking about, where all life came from. I'm talking about where you came from when you were a zygote. From being a zygote to what you are now, you don't believe there was supernatural intervention, do you?
Well, so again, you're talking about that relativity type perspective, now versus when either of us were zygotes versus what was before that. There's all kinds of relativity perspectives here. And so there's a good argument, or good, at least a debate on who you are. In fact, I follow my last boss's Neuralink project, where we're hoping to actually see where does the thought process, where does the quote unquote soul, does it actually exist in a bioelectrical, mechanical, chemical arrangement only within our brains, or is it somewhere outside of our bodies entirely? So all of those kind of questions are up in the air, and that's what we use science for, to finally understand. And so if our soul, if our being, our consciousness, whatever you want to call it, does not exist in our bodies now, much less as a zygote, where do you, quote unquote, come from? Where do you start?
So you're telling me that you don't believe in the science of embryology. We don't have enough evidence because of the mind?
No. In fact, there's wonderful examples of how the pre-codified, pre-engineered information function sets within DNA for all genomes, are pre-programmed, so to say, pre-codified to be able to change during the embryology, as well as even later in life, older age. There's all kinds of pre-programmed changes, and we can watch that. We can see, quote unquote, how you're knitted in the womb, as the Bible puts it. We can watch that now, not just physically on the outside, but also internally, information-wise, or I can't remember, programmatically wise.
That's not present in all life, though.
I believe so. What's an example you think where we don't see the formation of the from the first cell of an organism? Maybe
all single cell organisms?
Well, even those have to be copied, mitosis, whatever you want to call it, mitosis.
Yeah, but there's no developmental program in the same way as what Speed was getting at from a zygote.
Sure, but again, I apologize. That goes back to that relativity perspective. Somewhere, somehow, the first single-celled organisms were not single-celled organisms. There's still a development process. So whatever, excuse me, and you're right. It's not a zygote. It's not an egg and a sperm thing. But whatever creates the first cells outside of first cells, that's still the same point of origin. Same question.
I'm not following. I'm not following you. Say that again.
Well, yeah, there's different mechanisms for multi-celled organisms versus the single cell, obviously, but still the question, it's not so much of those kind of details, the physical details, what originated, or what preceded, what created, what started the first single cell's development cycle. There's still a process, a beginning, an origin, just as there is for multi-cells.
Yeah,
same question.
But that's not observable, in the present time. What we're talking about is extant species, extant organisms like bacteria,
right?
Like a mouse, like humans, like a fruit fly.
Right.
You can see a pattern.
Right. Which I'm sorry. I'm trying not to interrupt. Oh, right. So which is it's still as relevant as trying to find out the origin for the non-multi-cell. So again, you don't start as a zygote. Your mother creates the eggs, and then your father creates the sperms. All of that has causality. There's something that preceded all of that. So life does not start as a zygote. It starts well before that. There's something before the first zygote, and so that's the question mark. What started before the zygote? What started before the single cell organism? That's
what do you think? What do you think preceded the zygote, the sperm and the egg?
You're asking me or Speed?
It would be you.
Joel.
You are the guest.
Wherever all information comes from. So that's the religious question, either for or against God.
Okay, but let's. Okay, if I grant that God created your mom and dad, and they had sex, and there was a fertilized zygote. When we went from the zygote to what you are now, do you believe there's any supernatural intervention? Nestle just joined us. We're not going to gang up on you. thought we'd have. We were supposed to have immutable, but anyway.
Yeah,
So what I'm asking you is, do you think there's divine intervention in chemistry from the creation, from you being a zygote to you being a full-grown human being? Was there divine intervention there? I'll grant you that God created everything prior to you. Okay.
No, I could say, we can suppose so. If there's divine intervention to start it, what reason would there be that there's no divine intervention, in the middle or the end or whatever else?
So you think there's divine intervention in molecular biology today? Like
there probably could be. We talked a little bit about that on Tangelo's channel. We were talking about the cognizant ability of certain what certainly looks like fully artificial intelligent type algorithms built within DNA, and there's cognizant abilities inside DNA. So is it truly cognizant? Is it an outside? Is it actually thinking on its own? Or is it supernaturally directed? It's hard to tell. All we can see is that it's cognizant. It's making decisions and doing things that are exact opposite of random. So where does that come from? And then you got miracle healings. You got all kinds of
one thing. If I may point out something, like I don't think the opposite of random is like in consciousness. Like there are things that are random and non-random, and non-random does not necessarily mean consciousness, right?
I apologize. I didn't quite catch that, and I'm a little distracted with the text from James downward too. So please repeat that. I'm sorry.
Sorry. Like you made the you implied that non-random automatically means consciousness, like this decision making.
No. It doesn't automatically mean it. It just offers or allows the supposition for it, the ability, possibility, whatever you call it, the science of it.
Can you get more specific? I heard you describe these gene networks. What's the phrase you're using? Cognizant? Say that again.
Oh, yeah, the cognizant. There are functions within DNA regulation and just different aspects of code correction, error correction type stuff, memory stuff, archive backdated type, functions within DNA that look like they either have a mind of their own, or there's a sophistication within the programming that's beyond our ability to understand it right now.
Do you have a specific pathway, a specific genomic region? What can you be more specific? Like give an example of this.
Yeah, that was the first question. I think Speed. I think you asked me that night we met, and you were asking for documentation, and I know there's some out there. It's been a long.
I'm not challenging you as though you're wrong. I'm just trying to get more detail because I'm trying to place.
Sure. Yeah, like I'm saying though, I'm relying a lot on memory. So, from my understanding, things like retrotransposons, for example, they were once assumed that they were just randomly transcription errors that were jumping from chromosome to chromosome. It turns out now that they're not. That they're actually very specifically not only making their own corrections and errors within RNA transfers as well as on DNA horizontal transfer technology, but they're also basically doing archive retrieval. It's like they're a back-end service. It's like they're taking back-end data from histone collection groups that are normally, quote unquote, inactive, copying it and then moving it to or rearranging it to another active area, similar to how the RNA transcribes outside of the nucleus, but it's happening inside the nucleus. So, and it's not random because it still maintains a perfectly, a pre-engineered function. There's still something going on. It's not, again, 10, 15 years ago, well, actually, I don't think we knew they existed 10 years ago, but about 5 years ago, we assumed that they were mistakes, and it was just this civil war. One article I read years ago, but now we know it's not. It's self-aware. It's doing it on purpose to do other purposes. It's really crazy.
Okay, can you provide me a citation for that? It seems interesting.
Yeah. Like I said, I don't have active documentation on it. I'm not. I should have made this disclaimer too. I'm probably not as in-depth a geneticist as Speed or others are. I'm more of a information kind of physics guy. But yeah.
But what exactly did you describe as like they used to think that there was like a war zone going on? Like what?
Yeah, let me see if I can find it. I can try to link that one real quick. It's an old article.
Is it like spurious transcription or?
Well, what could we Google to find like something on that.
Yeah.
What-
Yeah, I just found this old article. This is from 2014. Civil War Inside Our Cells. Scientists show how our bodies fight off jumping genes.
Transposons. All right.
Yeah, that's what it used to be called. But now, again, and I don't know where I could help find things on the internet for the more recent research. You know, that I guess I just talk with people, you know, that are in this field, where they're not jumping genes anymore. They're active, cognitive. You know, they're doing things on for a purpose.
Okay, that's
No,
a Science Daily
still-
article.
They're still largely non-functional.
Yeah.
The principles surrounding transposons and retrotransposons, that hasn't been overturned. That's still the kind of the standard paradigm looking at these repeating elements. But what I think you're alluding to is evidence that some of them may have a function, but that would be a rare function. That wouldn't be the new rule.
And
That
that's
would
where,
be,
that's what I'm trying to
co-op
talk about.
by
That
the cell.
is the new rule. Yeah, there's research now that shows that there's no accidents. Otherwise, in fact, they're pre-designed specifically to fight accidents, prevent accidents, prevent the civil wars. This old article talks about.
No,
Okay,
I don't,
you don't
I
think
don't
we
think-
can fix? You don't think we can figure that out with molecular biology? You think it's something spookier?
What do you mean by figure it out? I'm not following.
I mean, you don't think this is just molecular biology? I mean, this is just these people that figured this out. Were they molecular biologists or were they mediums in a seance? It's what
that's ridiculous. That's irrelevant to me. It doesn't matter what your background is. I mean, information is information, but I mean, I don't know. All I'm talking about is just again, it's the apparent observation of cognizant functions within DNA.
To me, like I'm like skimming to the article right now. To me, they are still calling it jumping genes, but I think
this is 6 years old, right?
Right.
All right. And again, I apologize. I wish that maybe I can try to spend some time to find more current available public stuff. A lot of stuff's behind paywalls.
Well, do they mention anything? Do they link an actual article here? Let's see, story source content, University of Michigan.
Well, if they did, it could be old.
Here we go. Journal reference.
If you're reading any literature that describes these sequences as having a mind of their own, then you're not reading the actual the primary literature. This is an analogy. Maybe a journalist attempted to use to communicate to non-scientists. But
yeah, I don't know how you read my mind, but I'll say, for example, I am an AI programmer, and I've worked on projects in the past, and I'm still very interested in what the current efforts are today of trying to literally reverse engineer a lot of these processes that we see pre-designed in code to be able to augment and improve and create even new paradigms in our own information science processes. So that's why that's my interest in it. That's where I don't need to listen to what a journalist's interpretation of is. I can understand these things.
So what methods did you use as an AI programmer? What
methods?
Yeah, what
software methods?
Yeah, what model? What model were you using?
You asking what work I've done?
Yeah, what model?
More recently, I was working for not to give too much information, but I was working for an international financial management property management company.
Okay.
That were in SpaceX. I was doing a bunch of R&D work for scrubbing a bunch of data streams for rocket science projects. In the past, I used to work for RDEcom. We did a bunch of augmented reality, AI, machine language stuff for military training, and a few other things.
So you did like big data analysis, scrubbing data?
I did. And matter of fact, that's what I'm doing right. I just finished finished my MISM, and I'm working on a big data certificate right now.
Oh shit! What did I just do?
Pardon?
Oh, I just did something. I'm not sure what's. Hang on a second. Oh,
yeah. So big data is not really AI. It's just another. Yeah.
Right. Yeah. I'm trying to figure out what method you use. Like what? I mean, there are a couple of paradigms: neural nets and multi-level neural nets.
I think
is that what you did?
Yeah. I've done basically everything. I think if you really wanted to go into that, you can basically kind of summarize all AI functions into either it's either a heuristic layer or finite state machine type structure. If that's what you're asking. All the models are all spin-offs of those.
Okay.
And so for this case, oh sorry, I was gonna say for this case, we're trying to describe with the DNA information stuff is that'd be more of a heuristic layer. It's more of a decision tree type thing. It's not, and so yeah.
Yeah, we've got okay, so we got this article here, and they're talking about, but anyway, it refers to an article called ApoBC3A deaminates transiently exposed single strand DNA during line 1 retrotransposition.
Mm-hmm.
They're talking about something that protects against jumping. Basically retrotransposons. So
Right.
line 1 retrotransposons.
Yeah, I just read also the abstract of the paper. You can even click the link on that, and it's an open access paper. And I just read the abstract. It's about an enzyme that inhibits like a specific type of retrotransposons, and that's basically it. So that's a summary. I don't see anything that indicates a decision-making process.
No, there's nothing. There's nothing about neural nets or any. There's nothing like that here. So this
of course I'm not trying to overwhelm you with like harsh criticism. I'm just pointing this out. Perhaps you meant to give us a different type of paper that does show what you are saying.
Right. Sure, yeah. And just to kind of highlight on that, so that one particular enzyme, it's specifically trying to target and prevent a different other enzyme, and they detail it there about the middle of the page.
Oh, yeah.
So that's part of, and it's doing it to try to, and that's a particular enzyme they're trying to recreate to enhance cancer prevention drugs. But that's a decision process. It has to specifically seek those other enzymes to build.
If I'm not mistaken, retrotransposons specifically use a enzyme called reverse transcription. That's how they jump around in the genome. They use a reverse transcript enzyme, and I think that this enzyme blocks that enzyme from functioning.
Not necessarily. What's going on essentially is that the DNA is transcripting RNA, creating a normal tRNA process.
mRNA, maybe. Do you mean?
And then the transposons basically are reacting off of those RNA chains that then are basically reverse transcripted, I guess, or however you want to call it, to try to affect some of it. Basically, it's part of the error correction mechanisms, the automated antiviral and error correction subroutines within DNA. And again, this article's old. There's better research out there. There's one that I remember. The keyword was something about secret agent, for example. This one's Civil War. This one has like they're talking about there's like soldiers, and people trying to prevent the damage inside the DNA. This other article I remember, and I wish I'd kept copies of them for you guys, but there's all kinds of things out there where they talk about how there's like a almost a we call it a humanization, what's it called, Kelly? Anthropomorphic. Yeah. They're anthropomorphizing these functions within DNA. So
right. Which is probably something that you shouldn't do because that just leads nowhere. Anyway, this is actually Demeter's field, molecular alchemy. You want to comment on this?
I was just going to say the same thing earlier. I may have misspoke or may have been misheard, but I wasn't reading your mind, Joel. I was saying if you're reading any literature that describes molecular biology, genetics, as though it has a mind of its own, then you're probably not reading the primary literature. The secondary and tertiary literature, they use analogies to communicate to non-scientists.
Right. So to help clear it up, I've never, to my recollection, I have never read an article that said anything about them working on a mind of their own. That is for me only. That is I made that up in my own mind. Yeah.
Gotcha.
Okay.
Gotcha. Yeah, it's not clear exactly if there's any targeting. When these jumping genes. Maybe some of these others are aware of new data, but they seem to randomly insert in the genome at different locations.
Right. That was the old assumptions, right?
Well, it's not like purely random. Like it's not like, oh, like the transposon has an equal chance of inserting itself in every single location in the cell. Like some locations are more open to being, like, for example, like your genome is sometimes tightly packed in chromatin, right? So those are less accessible to this sort of stuff. So it's not purely random, but it's not also not very specific either. So it's more like it's like it's a better analogy, like a poker game, you know, like you it's not purely random, but also not purely specific either.
Yeah,
that makes sense.
Good debate. Yeah.
It makes sense, and it also, you know, there's probably a degree of selection where if they insert themselves into a essential, you know, regulatory element, that it would be lethal for that particular cell. So jumping to that, I'm sure there's hot spots and cold spots. They're not going to be jumping into essential genes because that cell would die.
Also, the article does mention that sometimes these retrotransposons do cause disease when they disrupt genes, but of course cells have mechanisms that that try to counteract such damage. Yes.
Exactly right. And there's a bunch more new research out there that it's just mind blowing. I think I need, just for my own due diligence, I need to collect more.
Well, that's a really good place for me to ask this question. I listened to you and John Maddox and Otangelo talk about how scientists were surprised and they couldn't believe what they found. And you guys were saying that for some reason you think molecular biologists do not think that the cell is complex, and that we were surprised that there's complexity and that we never went looking for complexity, that it just hit us over the head. But I wanted to ask you, who do you think is making these discoveries, if not molecular biologists?
Well, I wouldn't make that claim that you repeated from other people.
Oh, you're kind of agreeing with them.
No, I won't. I'm telling you now, I wouldn't agree with that. Okay. And then as far as the types of people or researchers or professions, whatever you call it, that designed this stuff, that doesn't matter to me. I mean, I've Elon Musk, he hired me as a rocket development guy with telecom video experience. Yet, even though that was the job title, I did everything. So, you know, and that's in science, we're always multidisciplinary. So it doesn't, you know, he could have hired me as a molecular biologist. I still would have done all these other things. But the people that I talk with, these multidisciplinary guys that are actually in these fields, even the biologists, they've told me that biology is useless now. You have to have a software engineering background like you and I to be able to even understand, you know, even pretend to begin to understand a lot of this DNA code stuff. So
I've got to strongly but politely completely disagree with that description.
Okay.
Computer science is definitely essential, and it spawned a new field of its own known as bioinformatics. And we absolutely rely on you know, computer specialists to design software to allow us to analyze data more quickly, to ask new questions. But the biology is essential. We set up the experiments. We ask the right questions. Without the biologist, the bioinformatician wouldn't have data to process.
Yeah, and see that's where and of course we'll disagree on that. So, you know, if I'm reverse engineering somebody else's code, I don't need to see the code output necessarily. I mean, yeah, I can help, you know, but you can derive the output by looking at the process. In fact, you'll better understand the process without necessarily being biased or skewed what you think the output should be sometimes.
Well, it sounds like what you're describing is, you know, you can do research in silico. You can use computers to figure out what causes disease, to identify novel treatments. Is that what you're saying? That the wet work is no longer essential, the bench work?
Well, I mean, I wouldn't say it's not essential. I mean, it's a useful whatever practice in science, and it's certainly I can agree with you that there could be certain other discoveries outside of the DNA side of it that you can help look for clues in the DNA. Because I mean, it's just such a wealth of information. You know, there's no way any one person or even group of people are going to understand the whole code. But it's like a library. So yeah, if you can find something else that we can look at different sections of different books in, that's certainly a helpful thing. But as far as understanding the processes is what I'm saying. You know, you can watch, you know, the RNA or even the ribosomes doing certain things. Yeah, you can watch it and you can describe it and you can give it names, but you don't know what it's really doing until you look at the code.
Code is, but the way you look at the code is what molecular biology. That's how they're making all these discoveries. They're going into the lab and they're crystallizing and X-raying and poking around and trying this and that, and that's how we figure this out. That's how the system has been figured out.
Well, if I recall, sorry, go ahead.
My bad. I was just saying I was agreeing with that. Just there's a software engineering element to that to be able to do those processes, right? Go ahead.
Well,
if I recall correctly, like there was a scientist who like made genes with like a triple U, for example, and he deduced, this like triple U codes for this amino acid, and then of course step by step, they figured out which codons code for which amino acids.
Well, that's basically
it's still a bit of a wet work to figure out. Of course, well, of course, you don't disagree with that, of course. But anyway, go ahead, molecular alchemy.
Well, I mean, the computation is really the way that Joel's describing it. It's the biology is secondary to the computation, and that's, from my experience, that's just flipped on its head.
Yep.
You can model things in silico, but that's not considered rigorous until you actually put it into cells, you know, manipulate cells, actually show a change in phenotype. You know, they're intricately linked these days, but the wet bench work of biology still drives biology.
Okay, yeah, and I would love to have a conversation with that with you someday. It sounds like a fascinating question. Again,
Sure.
The things that I'm saying are from other molecular biologists that say, yeah, and I agree. There's all kinds of wonderful. In fact, we were sharing on Intelligence channel. That guy, I forget his name already. I apologize. He was showing some sort of X-ray, super zoomed in version of the motor transport protein, and that's amazing. That's fascinating. We have all kinds of assumptions, of
that was a model
works in the code. We reverse engineered how the proteins work, but to actually see it on a biological, microbiological, whatever you call it, scale, that helps confirm the science. Essentially, it's not. If I said it's useless, I apologize. It's just not. Biology requires software engineering. Essentially, is what I'm trying to convey.
Mainly for handling large data sets.
Yeah,
that's the main use of it.
Yeah.
Processing gigabytes of data. It's not like discoveries are being made by a computer. I don't know any biologist who could just sit at their office, and cure cancer.
Right.
Which that's a little hyperbolic. That's not exactly what you're saying, but
like the software is used to process and interpret the vast amounts of data that is fed in from the wet work.
Well,
it's
sure.
Still,
even
if you look at
data. Sorry.
The computation honestly is secondary. It's field by field, but in something like human medical research, I mean the disease, the computational side. Just look at funding. You're going to have a bioinformatician on there, but the type of grants that a bioinformatician in general would write would be novel algorithms or integrating data sets from multi-omics, proteomics, genomics, metabolomics. But the actual biology is still, it's wet, hardcore, get your hands dirty bench work. And it drives the state of the art, not the other way around. I mean, we can move on to another topic. This is kind of an opinion about the current state of affairs.
Oh, if I may, like to bring back a older topic a bit, like when I was still in the live chat listening to this, you said like like something to the effect of just a theory, and I don't know specifically what you were talking about, but you said just a theory. So I have a bit of a problem with that phrase, of course. So, for example, I think you mentioned chaos theory in another talk, and that is also just a theory. So it doesn't make much sense to say just a theory, right?
Yeah. If you're asking me a specific question, I'm afraid I'm not following. But
like you said, you made a rhetorical like I don't know what you were talking about. Like you said, oh, it's just a theory, as if it's like as if a theory is a bad thing, but a theory is still a good thing in science, right?
It was in relation to evolution and the implication.
Oh yeah,
and that's our inference. But the implication was that the theory of evolution is largely speculation, not hard science. And that may not have been your intent, but that was kind of how it came across. Because I heard the same thing.
About that was before this conversation.
Yeah, I know. Sorry for bringing back
age of things, age of the Earth, for example, the theories behind that. But as far as evolution goes and the theory of evolution, again, the scientific method, as Bacon postulated it, at least, is to have empirical, repeatable evidence in real time. So to base something that's outside of real time it doesn't meet the what do you call it, the criteria of a scientifically empirical, whatever you want to call it. It's still theory. I still have a problem with you saying it's still a theory. You cannot. There's all kinds of. We have a theory that we're going to be able to frack the carbon dioxide on Mars and be able to breathe it here within the next couple of decades. It's a theory.
Maybe this will get clarity, Joel. In the hierarchy of assertions or statements of fact, how do you rank a scientific theory? In compare relative to other claims.
Well, like I just said,
do you think it ranks low or high as far as the amount of confidence you should have in what the theory states?
So you're reminding me of Albert Einstein, the way he put that. He said that no matter of experimentation can ever prove me right. A single experiment can prove me wrong.
Yeah.
So the only criteria that I'm talking about again is it repeatedly observable in real time? If not, then keep looking at it.
So that Einstein quote is referencing Popper's falsification.
Yeah.
You can reference anything you want, as far as I'm concerned.
and the philosophically, what it basically comes down to is that science doesn't prove anything beyond a shadow of a doubt. It simply excludes things to the point where what's left you can have the highest confidence in, to the point where you can have higher confidence in that than mundane everyday things or other claims.
You're describing basic deductive reasoning to me, and again, that like Einstein was saying, that you can overturn any deductive conclusion on its head by some new piece of evidence. That's the fun of science.
I think you meant inductive, right? Or maybe I'm wrong.
Well, it can apply to both.
I'm also a philosopher. No, I also not know. Sorry.
I think it's
Joel. The way you're describing it, though, and this is a common tactic used, and this may not be intentional on your part, so give me a moment. But the way you're describing scientific theories is as though scientific theories have no additional merit, and that there's no reason to have higher confidence in scientific theories than, say, a hypothesis or some other rubric. Is that your position?
I would say that the hypothesis is the same as a scientific theory. I'm not sure what you're alluding to as far as what other people
I will, if I may, I will cut to this chase. In science, a word theory is different from what most people would say theory. I have a theory that most often describes an idea, but in science, it's the highest confidence that they can achieve. Like That's
Well-
like Einstein's theory of gravity is still a theory, but it's a well-supported hypothesis. That's the whole point of what a theory is. So
Okay.
if you say just a theory, it's almost like you are degrading what a theory is, even though it's the highest confidence that science can achieve.
So you're basically asking how much faith to put into a specific theory.
No, not
Confidence.
faith, confidence. Like when something becomes a theory, it is supported by an overwhelming amount of evidence. Like, for example,
It's irrelevant.
Pasteur's germ theory. Like,
Mhm.
would you say that germs are just a theory?
We have repeatable, observable evidence of
Right.
how immunology and microbiology work. So
Yeah, but it's still a theory. It's still a theory. That's why a theory is
theory
like
is repeatable evidence. That's the difference with the scientific method.
I think we might as well move on to another topic
Yeah,
because
right.
Well, I was thinking I got analogies I could share if it helps.
I think you
I would-
effectively communicated your position on this particular topic, and I don't think you'll find agreement with us.
That's fine. It sounds like you guys are kind of maybe making other people's arguments other than my own too. So, but if we want to clarify it, I'm game for it. I'm up for it.
No, I'm referring simply to what you've said in this. I haven't seen any of your other content, so I'm just referring to this talk.
Well, if I may, okay, unless you guys really want to move on, again, I've got some analogies that I've been thinking of here the last few minutes. I'd love to share as an example.
All right.
So, earlier, what were we talking about? Oh, like the DNA to software engineering example, for example. I just said example twice. It's weird. To be able to understand the code is prerequisite to understanding the process that you observe in the wet works, as you put it. So, as an example, I was thinking of, again, working for SpaceX, the Falcon 9, the Falcon Heavy modules. We have an AI that helps the rocket system, the avionics package, to self-land itself, right? So that's a process. So we can watch the rocket, go to orbit, come back, land, and try to gauge how the process should work based on the success and failure rates and all kinds of wonderful stuff. But as soon as you crack the top of the first stage booster open and you break in and you log in, you connect your computer, whatever you got to do to interface into that information, that parent cognizant information that actually helps it do that process in real time, you really can't understand it. And once you log into the AI and you download it and you look at it and you analyze it, then you can say, okay, well, this is how it's supposed to work. And then whether we see it work or not is a whole other story. And then as far as like the theory goes, the theory behind evidence, I was also thinking like with the Falcon Heavy, we did the first maiden launch, was it September or so, February, or I forget, 2018. And that was a beast. We worked so hard on that. It was 2 years over schedule, and it was a theory. You can look at the Falcon Heavy launch as it was a theory this should work. We got tried and true Falcon 9s. We spent over a year trying to figure out how to make them connect, and the little things that I forget what they're called now. The things that the separators, once you launch to release the side boosters, etc. We spent millions of dollars trying not to spend millions of dollars trying to figure out how to make that work. Oh, I'm sorry.
Okay.
And it was very, very frustrating. It was all theory. It's never been done before. All these things we were developing. And so it got to the point, launch day, Elon literally told us he's going to be happy if the thing just makes it past the launch tower. so that's what I mean. When you say scientific theory, we theorize it'll make it to orbit. And it was. We actually, we will claim, those of us that were there that did all that work, that was a miracle to us. It was a pure raw miracle of God that thing we only partially lost one booster. It should not have done that by all reasonable, whatever you want to call it, scientific hypotheses, theory. But it did.
I think the way you use the word. Oh,
oops, hold on,
sorry.
Someone trying to talk, but it's not. Hold on, my Bose system just turned itself off. I apologize.
So yeah, I agree with the other person who was speaking. I think there's a little bit of equivocation here as far as kind of common parlance theory versus scientific theory. I think we can move on to another topic though. Speed, did you have?
One thing I want to say, like the
Go
way
ahead.
you use the way that you use the word theory is equivalent to the way that hypothesis is used in science.
That's
And
exactly what I said earlier, right?
yeah, but the word is like a theory in science. Theory is referred to something that is even higher, quote unquote, than hypothesis. It's an explanation that is well supported, basically.
My 25 years on the bleeding edge of science and technology, as I call it, I would have been fired if I said that a theory is different than hypothesis.
Really? Wow.
Same thing. They really are. Even a quote unquote, there's no such thing as a scientific fact either.
Were you working for China?
Yeah, I was working for.
Wait.
I've been doing all kinds of crazy stuff. But regardless,
I've got to ask for clarity here. Are you? I may have misheard. Are you adamant that a scientific hypothesis and a scientific theory are the exact same thing?
Yes. I don't understand anybody else.
Yeah, you're wrong. Sorry.
I think we can just move. I mean, it's people use words differently, and I think
science
short of well, apparently we do. Short of extended
theoretical.
Short of. So say that again. Define a scientific hypothesis.
Is a theoretical hope. You come up with a reasonable hypothesis / theory, and then you try to see if you have evidence for it or not.
I encourage you to check the literature, like introductory.
Yeah, read about that one because that's not
science philosophy.
Einstein's theory of gravity is not just a mere hypothesis. It's a theory, and a theory means it's very well supported explanation.
No, it's incorrect. We don't even know if gravity is a wave or a particle or both, and we've got 3 different versions of gravity. That's part of what it is SpaceX as well. I had to do the equations to try to combine, classic versus relativity.
So you think that gravity is just an hypothesis, like?
Say again? Yeah, no. Gravity. We observe what we call gravity. We observe particles and large and small objects that have gravitational effects, but we still don't know exactly what it is. And there could be a wonderful discovery that finally, like LIGO, for example, they're trying to determine, is gravity a wave or not? There's other projects that they're trying to see if it's a particle or not. It's still up in the air. We don't know for sure. We observe it. We have observations, but we don't know exactly what it is. We're trying
I think we are revealing a fundamental misunderstanding of science that you have. But anyway, I think we need to move on to a different topic.
I would if you want to do low and high orbit spatial relativity equations with me someday, which really, really suck. But if you want to do it, you got to combine all 3 different versions of gravity to hope to do it, to help to predict how to get those signals to communicate properly. It's a headache. There's no straight narrow path. There's no solved equation. It's all theory still. Well, go ahead. Yeah, please. If you want to talk about something else, by all means.
Okay.
The other guy is gone. But anyway, I'll go ahead.
You said you had a background in inorganic chemistry, or that you actually went to school for inorganic chemistry?
I did.
And you mentioned something that confused me. You said something about phosphate baths.
Yeah.
Like a phosphate bath where nucleic acids would turn into polyphosphates. Can you elaborate on that?
Yeah, that was one of the reasons why I quit.
You quit? Okay.
The degree on, but yeah, I was asking Dimitri about that too. I've been asking it for 20 years. So yeah, nucleotides or monophosphates, they've got that phosphate backbone. And the weird thing about it, so once you have a formed nucleotide bond, then yes, you can. We watch in real time the observable mechanics to basically copy that, unzip it, and create new ones based on those bonds. The problem though is if there's other phosphates floating around, quote unquote free floating phosphate bath, as they call it when we did the experiments on it. Then if any of those phosphates get nearby, like another like one of the loose hydrogen bonds or one of the sugar bonds, that it will snatch onto that phosphate and then will instantly react into just almost random polyphosphates. So it's like how does this stuff form without being pre-organized, without being pre-made?
Well, it works in the cell, right?
Well, that's just it. So it only works in the cell because it's already made. And
Well,
so
it works in vitro too.
does it?
Yeah, it does. I don't know where the phosphate bath comes from. What is a phosphate bath? You mean you put phosphoric acid in, like you bathed it in phosphoric acid and it did something you didn't expect?
No, any phosphate molecule. So like the mitochondria, for example, is what,
phosphate molecule.
yeah, that's what in the DNA in the cell. That's what the mitochondria and then a few other processes. I think for the cell types that they don't have mitochondria, they do that. They segregate. They make sure there's only a specific phosphate group nearby the nucleotide, the nucleic acid, to make sure the nucleotide chains don't turn into something else. But if you don't,
well, that's how biology works. There are enzymes that
but
specify.
If you don't have biology, how does it work? How does it work outside of
biology? Then you just have a bath of chemicals. I mean, you can do anything you want. But I don't understand how that had anything to do with evolution.
Well, it has to, and that's the origin of life questions. So again, life does not start with biology; it starts with something prior to biology.
So you think the Earth was a phosphate bath?
Not at all. No, that's ridiculous. There's no. I mean, there's phosphates on the planet, but no stellar object is required to be a phosphate backbone like nucleotides are. We're talking about nucleotides, not the planet.
Right. So we're talking about abiogenesis, briefly, but I was confused by your comment, and I'd never heard anybody say anything like that before in my life. So
tell me about it. It's what's so frustrating. I've been asking about it. When I started, because
I can see why you're frustrated.
Well, have you asked origins of life scientists who are studying this?
Yeah, did you ask Demeter? Well, you were talking to him when you said it. How did he respond?
I asked him about it, and I had to go drop my son off at work. I came back, and he just left. Just quit the channel. I was like, "What? Wait a minute. He promised he was going to tell me." But no, I don't know if you heard more of my background. I started my ChemE degree while I was already working as a plasma physicist for well, I'm not going to tell, but and so I was already doing the science. I was already doing a lot of the math.
You were a plasma physicist?
I was. Quantum plasma. I was doing wet and dry etch for microchips and MEMS and nanotechnology, and we can talk about more later. But basically, I was already doing that field, and one of my senior engineers was like, "Well, why don't you go get your degree and you get more money?" And I'm like, And long story short, we teased each other about it. So I go to the little state college there, the university, the prominent university, and they're talking about this. They talk about the organic chemistry, the molecular stuff. I was doing both the chemistry and the biology classes, and I'd ask my professor, "Well, wait a minute, how can we do this experiment? Can we show how this happens? How do you prevent the phosphate bonds from destroying these other bonds?" And he just looked at me like you just did. I've never heard anybody ask that before. And so some professors really hated me asking that question. Other professors loved that I asked that question, and I got invited to all kinds of federal, national research projects and whatnot. And it turned me off because not only could they never answer that question, they didn't even bother to ask those kind of questions, but everything that they were teaching was 20 something years behind what we were doing in inorganic chemistry for nanotechnology. And it was like, okay, why am I going to school? Why am I doing this? So I switched paths, but regardless. Yeah. So I'm constantly trying to, if I find anybody that has a good, even modicum knowledge and education into organic chemistry, which is not my strongest suit. I mean, chemistry is chemistry. I want to see if they can help answer that question. I can't seem to find anybody that knows.
Well, molecular alchemy has a PhD in molecular biology.
Perfect.
Yeah. And Immutable Destiny, who chose not to be here today, is a biochemist.
Right, and that Dimitri guy said he was an organic chemist, I believe.
No, he's a molecular biologist, geneticist. And these guys actually work in the field. They actually work in the laboratories. So.
And I would love to hear their explanation.
Oh, you want to explain that, molecular alchemy? Why the phosphate bath and the idea of free-floating hydrogen bonds?
No, phosphate bonds.
Maybe a free-floating phosphate bath, and you said loose hydrogen bonds, which
hydrogen is very loose. So the phosphate, if there's already a phosphate in the chain, and another phosphate comes by, I think it's supposed to make the hydrogen be able to move around and all kinds of the sugars as well.
I guess I don't understand why this is a problem, so I don't know.
Yeah, I'm not sure exactly what conditions you're describing, Joel, but I mean, these biomolecules exist in the presence of all kinds of other organic compounds in the cell already, and we go ahead.
Oh, go ahead. No, I did not mean to interrupt.
What were you saying?
Oh, I was going to say, yeah, they're once the nucleotide is made.
We can. Sorry, there's a delay.
Yeah,
go ahead.
I apologize.
Hey, we're being so polite. We're trying not to step on each other's toes, but there's a delay. Okay. So go ahead. Give more details about the conditions you're describing, because I think I missed some of it.
Yeah, basically, how does it happen outside of the cell? Because like I was telling Speed, the nucleotides in the cell, they're already pre-made. And so, yeah, we understand the process of how preformed nucleotides, monophosphates, are able to be basically taken apart and put back together. You know, the whole mitosis process and transcription processes, we can see that in real time. We understand that. But how do they happen before the nucleotide bonds are solidified and the energy barriers are in place? Because if you put a bunch of phosphates near, you know, a non-exist, or basically just nucleic acids, essentially, without before they form into a nucleotide bond, then they'll instantly react into polyphosphates. As far as all of the chemistry that I've understood and trying to ask these questions over the years.
I'm not like you. I don't really understand what you are specifically describing. Like you have like nucleotides, right? Like just the monomers, like with the base and the sugar and the phosphate, and in the presence of other phosphates, then they will form like a long tail of phosphates, like on the nucleotides.
As long as the bonds are already in place, they will. But if the bonds are not in place, then they will react into polyphosphates. You basically have to start the chain. You have to start the zipper for it to stay a zipper.
I don't know. I don't know. Like for example, the you know ATP, right?
Yes, that's a polyphosphate.
There's a polyphosphate. Like when ATP is the energy currency of the cell. Like it is formed from ADP, which has only 2 phosphates, and going from the
mitochondria, right?
And going from ADP to ATP requires energy. So it doesn't happen spontaneously. So you're saying that making this chain longer happens spontaneously, but ADP from ATP or from ADP to ATP requires energy. So I'm not sure if you are right on that.
Well, because a nucleotide has nothing to do with ATP. That's a monophosphate versus a polyphosphate. That's an entirely different chemical reaction.
But the addition of a phosphate to another phosphate is pretty similar, whether it's ATP or if it's a nucleotide.
Yeah.
So on a nucleotide,
you mentioned.
Go ahead.
So are you talking about a reaction between the oxygen of one phosphate group,
or any of them? Mostly the hydrogen seems to be the biggest problem.
Which hydrogen?
Oh gosh, I forget which position it's in. Let me look it up. Peptide. Yeah, there's a open up that picture. There's the ammonia. There's the OH on whatever I forget all this stuff. See, again, I'm not an organic chemistry necessarily. So I know these things that have names for them, but the picture I'm looking at on Wiki, for example, there's an OH molecule, there's a NH2 molecule on top. So before they form this molecule, those hydrogen atoms and ions are loose. They're not in this chain. So when the phosphate that's connected to the oxygen atoms interact with these other pre-chained other atoms, it will create something other than a nucleotide. Because the bondings are stronger with the phosphates than with the other ones, especially the nitrogens. Nitrogen probably being the most strong bond there is. So it works as long as the nucleotide is already formed. Once you've got a nucleotide, you can make more nucleotides. That's a given. The question is, how do you make a nucleotide without a nucleotide?
Wait, how is it a given if you have one nucleotide? Like the presence of a nucleotide promotes formation of additional nucleotides?
Yes, because we see that in real time in biology. That's a given. We see that. Like I said, mitosis, transcription, it happens. That happens in multiple different varieties, and it's a wonderful chemical reaction. And it's fascinating. It's never found in nature. It's only found in living cells.
Once you have nucleotides, I'm really difficult to understanding what you were saying. Like, can you maybe perhaps bring up a graphic to?
You're talking about like abiogenesis, about how the DNA was formed, and you're going back and I don't know what the hell reaction you're talking about, but it has nothing to do with abiogenesis. I mean, it's one of the possibilities, but I mean, the abiogenesis goes a lot further back than that, for one thing. And
yeah, no, I agree. We got Hoyle's still,
and that isn't the only thing that happens in the cell.
I wouldn't say
it happens because of enzymes rather than. I mean, if you took the cell apart and put all these chemicals in little flasks, or churned them up in a mixer, right? You'd have a problem, because we have to have a cell, right? I mean, we're talking about life, and you're talking about the beginning of life, and you're not making any sense at all with what with your question. Basically, is my problem. Okay. So I think we should move on from that. But I was just curious about that. So.
Yeah, no, the basic process of what they call reverse engineering is to take what you have as a process, try to see what the process is before it happened, lead up to how the current process is, and that's part of that. So we've got a nucleotide.
Yeah, but wait a minute now.
New nucleotides, but we don't understand. In fact, based on my understanding of chemistry, a nucleotide cannot form without another nucleotide. It's not that we don't know how, or that it's improbable, like most people say. From all the conversations I've had over many years, especially with my own professors, with every other professor I could find, we come to the conclusion. You're right, Joel. It can't happen. How did it happen? This seems physically impossible.
Do you deny that there are processes that can make nucleotides from simpler compounds?
No, a nucleotide can help make other new nucleotides, but
from simpler compounds, like.
Right, that's the question mark. From our
I actually am aware of a paper that shows one way how this can happen.
Well, if you're gonna
there's a lot of papers on how polynucleotides are formed.
I've heard that argument before. That's ridiculous. Life is not
ridiculous. Why is it ridiculous?
You're talking about this natural formation of inorganic peptides, the NH-O type.
No, polynucleotides. I meant. Did I say peptides?
I'm just saying that's the argument I've heard before. Basically, nylon makes DNA. Like, no.
What? Nylon?
I've heard that argument. I was just kind of jumping the case. Yeah.
What does nylon have to do with it?
It's a peptide nucleic acid. It's a plastic that self-forms itself.
Yeah.
But it has nothing to do with life. It's not a nucleic
acid. No, it's not. I believe it's not a nucleic acid. No, it's a peptide. It's a peptide.
Right. There are.
Nylon is a peptide, basically, or it's an polyamino acid.
Yes,
but different kinds of polyamino acids has nothing to do with life.
Exactly my point. I've heard people try to assume that different types of nucleic acids or whatever, that there's other plastics out there that can self-form their own structures, and so they assume, well, if plastic can do it, why can't nucleotides? I'm like,
well, they can.
No, it's a entirely different reaction.
What?
It's an entirely different set of chemicals and reactions and bonding. It's apples. It's not even apples and oranges.
How do you think that life makes new nucleotides?
By copying it from pre-existing life.
Wait, do you think that nucleotides are made during the DNA replication process? During that, like when?
Yes. So the nucleic acid.
No.
They're made in the mitochondria normally, and then they're refloated back through the nucleus membrane.
Yeah. They are made somewhere else. Not like they aren't made on the spot when the DNA is replicated, right? They are not.
No, from my understanding, the nucleic acids themselves, like the other polyphosphates, they're made outside of the nucleus. They're brought into it through really crazily, again, more AI type mechanisms. And then once they're inside the nucleus, then there's other proteins that basically really unzip and then rezip. And so the nucleotide bonding has to exist. And then there's all these carefully pre-programmed, machines, little machines, protein machines that make sure that the connections are undone just perfectly and then redone just perfectly with the available nucleic acid. And it makes a perfect copy. And if it doesn't, if it makes a mistake, then there's all kinds of really cool little again, AI algorithms that send signals to other things that come in and repair it.
No, not AI algorithm. No, it's not AI. Anyway, let me interject. Nestle, I just gave you a wrench. Can you put the link for this paper in the chat?
Is it? I guess I don't remember the paper, but this is just a figure. Okay. A figure from the paper, but I can look up the paper in a few minutes. But it basically shows, like, although I myself have some problems with this paper, but anyway, this is at least one way of how nucleotides can form.
Right. So the question mark, the challenge is, you take that picture and you throw a bunch of random phosphates or anything else in there outside of these perfectly pre-segregated little chemical bondings, and it blows up. Becomes a polyphosphate.
Yeah, if I put sulfuric acid on it, it would also blow up. But
well,
I mean,
that's fine. But we're not talking about sulfuric acid. We're talking about phosphates. Those phosphates are required for this reaction. If you put too many phosphates in here, which is what we would assume to have to happen naturally.
Right. If we dipped it in phosphoric acid,
they actually added phosphates on the last step. Like, for example, the first thing they try to figure out is how do you get, like, of course, wait a minute, where is my? Do you see my cursor?
I thought nylon was a plastic, not a sugar, but go ahead.
Plastic?
Plastic?
Yeah, it's plastic as in a polymer.
It's a polymer, yeah.
Not a sugar.
But it doesn't have anything to do with any of this. But yeah, I still don't understand your point.
The first pathway they tried to figure out is the blue one, but the blue one leads to an X, like the red X that you see on the figure leads to a dead end. These two won't react. But for the green pathway, when you have like simpler compounds reacting in a different way, and then in the last step you add a phosphate, then it will spontaneously produce the nucleotide in the presence of phosphate.
Right. In a perfect, white paper where there's nothing else involved. Right. If you put other atoms in there, it won't happen.
Yeah, but how do you know other atoms were in there? I mean,
that's the natural state. We don't have a natural state of just nucleotides.
Okay. Have you heard me referred to as speed of pudding?
I think so. What does that mean?
Okay. My point is that it wasn't pudding. All the molecules aren't there all at once. You don't throw all the molecules into a flask. I mean, there were many varying conditions involved in abiogenesis. But I mean, well, if I had time here, I could probably pull up. We have 1,000 papers. What is it? I think 10,000 papers in the last 10 years on abiogenesis, and a lot of them are about polynucleotides forming and polypeptides forming. And Demeter did a very long talk on a methodology where things started very, very simply from prebiotically available chemicals and showed a pathway for all of this to happen. So anyway, I think we should leave this alone for now because you're not going to yield on this. You think you got something here, but so far you have kind of been talking nonsense as far as chemistry goes. So.
Yeah, that's rude. And again, I was wanting to try to say how that's what I was doing back when I was doing chemical engineering. Was a lot of these.
Well, if you want to send me papers or a paper on this, or maybe send me some, write down the equations. Tell me what you did. What did you put in the flask?
I'm still wondering about, like, what you mentioned about adding phosphates. Like, if you add more phosphates, then it will add more phosphates on the nucleotide. Like, do you have like maybe a link to something that gives a more detailed explanation of that? It's a simple
thought experiment. So in cells, there's a vast nanotechnological factory that makes sure that there are not free-floating phosphate bonds floating around that will mess up all these reactions. It's a very
that's
careful
not what I asked. I asked like, maybe do you have maybe a link to something that explains that more in detail?
Probably.
Because I have a difficulty in picturing exactly what you are talking about.
And that's what's so frustrating. So again, when just a 25-year-old kid, that's doing this kind of stuff, in the field, goes to school, and no one asks these questions. So regardless if we can find a paper on it or not is irrelevant. We can do our own thoughts.
I'm not asking for a paper. I'm asking maybe for like a link to something that explains what you are saying.
A web link is a paper. It's an HTML piece of paper.
Okay.
But regardless, I mean, that's the question mark. And if you guys can help think about it, I would love. Again, I've been asking for years. My understanding is that you, unless you've got some other.
Am I not clear? Like I'm asking a very simple question. Like I'm asking for something that that explains what you are describing more clearly.
Right. Just take what you showed earlier and add more phosphates randomly in the picture, and it will instantly react to a polyphosphate.
Again, I'm asking you to provide a link to something that explains it. Like you're not answering the question.
I can write one, I guess, but regardless, we can sit here and do it in our own lab right here, our own thought process.
Am I speaking like not alien or
you're
something?
You're asking for a paper, and then you say you don't want
No, I'm asking not necessarily a paper. I'm just asking like for a link to something, maybe a book page or whatever. Like a Wikipedia link, whatever. Something that explains what you are describing, because I have difficulty in picturing
traction.
Use your paper that you presented earlier here today. Use that exact same web link that had the beautiful process and the linking for the different nucleotide chains, and just add things that are not part of the nucleotide there, and see how it's not going to react into a nucleotide. That's the problem.
Yeah, but what are you adding? You're adding phosphoric acid?
My specific question is other free-floating phosphates, because again, like I was trying to, and I've been repeating myself. There are very carefully pre-designed processes throughout every living cell that tries to make sure to regulate and limit the amount of phosphates in any particular area, particularly around nucleic acid creations, so that specifically when they are recognizant within the actual DNA, the actual nucleotides and things like that, that the phosphate is already basically where it needs to be by itself without any other phosphates nearby to ruin it all. And also the pre-bonding, the energy barriers already associated with the pre-existing nucleotide help prevent any of those other accidental little phosphates. Well, none of that happens if the nucleotide's not already formed.
I really have a difficulty in understanding what you're saying, because
chemical bonding is all it is.
Yeah, but you like, it's almost like you were saying like, oh, this can just form a bond here and here and there and there, but I'm like, it's not like
chemistry. That's covalent bonding.
Of course, chemistry is not random. Like it doesn't say it can form a bond here, form a bond there. Not necessarily the case. But I'm sorry. I'm a bit frustrated because I repeatedly asked you for something that explains what you are describing. In
so third time's a charm. Take the chart that you already showed us.
But that's not an answer. I can add a pixie there. So it doesn't answer my question.
Which is what again? I'm sorry.
Like what you are describing, like adding phosphates to the nucleotides. Like can you describe, like point to me a paper or a book page or whatever that describes this problem.
Yeah, we only see nucleotides ever in the entire universe. They only exist in cells.
I give up.
Nucleotides exist outside of cells.
Yeah, I give up. I've asked this question 10 times, and it cannot give me an answer.
That is the answer.
I'm asking you for something
pre-existing bonding.
I'm asking you for something that explains, like a book page or a link to a paper or whatever that explains what you are describing.
Again, it's real simple chemistry. Take what you showed.
Am I not being clear? Like,
we know how nucleotides form. We know how they
oh my god!
They require pre-existing nucleotides to maintain that structure. So if you don't have that structure, how do they form? That's
we have counseling services available Standing by.
I'm sorry. Like you really are a nice guy. We can have a nice conversation, but it gets so frustrating when I'm politely asking for something that like visualizes or explains it in more detail what you are describing.
Okay.
Like
here's an example. Say, for example, car engine. There's a wonderful pre-existing structure for a car engine, all the components, the way it connects, the way it's designed. So, how does a car engine form outside of a car?
What the hell has cars to do with nucleotides and phosphates?
I don't know how to simplify the question anymore. All I'm asking is how does a nucleotide form?
What was my question? Can you relay the question that I'm asking you? What?
Nephilim free atheists get frustrated when you talk about science.
No, I get frustrated when somebody doesn't answer my question.
Yeah,
with a straight answer.
My question is, how do nucleotides form without nucleotides?
How do they form? I gave you a paper to that. So yeah.
I don't have a paper. I could make one. And again, whenever I ask my professors and other biologists for 20 years, they're either like, "Wow, you're stupid," or "You're right, Joel. They can't form." That's the only conclusions I've got so far.
Okay, I have enough. I have enough. I have
wasted my time. I think
I have enough to look into this a little bit and maybe come back at you with something. So let's just move on. Let's move on. You said something interesting. You said the histones were universal in life.
My understanding is there a non-histone packaged DNA chain?
What's that now?
Is there life out there that does not use the chromatides?
Yes.
Like what?
Prokaryotes.
Let's look that up together.
Hey guys, can you hear me?
Yeah. Do you have any connection problems?
Molecular, yeah. Do you want to address this basically histones and the epigenetic code and and that it's not universal in life? We're moving on to another subject because
if I may, like one last question, but differently phrased, like the problem that you are describing, like with phosphates. Where did you read that from? Like, did you read it from something?
I thought of it myself.
You just made it up, really.
Yeah.
You just made it up. Oh my god! Oh my god!
That's how scientists work, dude.
No, it doesn't.
That's like counselors are standing by.
How dare you?
Nephilim free in the side chat. He said that you were talking science a lot, but it turns out you were just talking out of your ass. My god.
I'm asking questions about our understanding.
But you cannot say this is a problem if there's no basis for it. Like you are just describing a random thought that you had.
Why you're criticizing me for asking questions?
Here,
but the problem that you are describing is just made up.
Doesn't matter. Scientists question everything.
Joel, give us a second. Let's get back on track with being cordial and patient. I think what Joel is saying is specifically about prebiotic conditions that in a pool that contains by all means correct me once I finish this, but in a solution that contains phosphates and nucleotides, you would have competition, or I guess he made the distinction before a nucleotide is present.
Yes, sir.
How do you have a phosphate group added to to form a nucleotide when all these other phosphate groups are floating around that it could interact with? And is that along the lines of what you're saying, Joel?
Yes, sir. So before a nucleotide is a nucleotide, it's a collection of nucleic acids that form a specific monophosphate bond. So if you've got multiple phosphates in the area, almost random areas, where in the wrong place at the wrong time, it will instantly react into a polyphosphate, which is useless for life. So that's where I'm trying to find out how to auto-arrange without pre-existing nucleotide.
I don't know the chemistry firsthand, this particular chemistry.
My question is this: Do you know that it will spontaneously produce polyphosphates, or did you made it up to?
No, that was what that's exactly. We do know. That's what we That's where the debates basically. Or the
Can
question,
you show me something that shows
Well,
that it will spontaneously form
I can't hear you over me, sir. What?
What energy source would add one phosphate to a second phosphate?
Yes.
Then the bondings themselves, the covalent bonds between whatever connected where. That's how covalence works.
That answer makes no sense at all.
It's just covalent bonding. It's basic chemistry.
Yeah, but he's asking where the energy comes from to make it bond in the first place.
Yeah, it's covalent bonding.
But you have to break a covalent bond to form a new covalent bond.
Yes.
Not necessarily. You know, when you have non-bonded.
No, it's oh my god! You don't know basics of chemistry. Oh my god!
No. See, when you have free-floating atoms or like a phosphate
These
group,
aren't atoms. These are molecules. These are phosphates.
Phosphates are not atoms; they are molecules. Oh my god!
So you have atoms or phosphate groups, like a phosphate. They'll bond to other things. They don't necessarily need more energy. There's already energy within the atomic.
But in order for a compound to form a new compound, you have to break some bonds in order for new bonds to be formed. That's a basic rule of chemistry.
Well, they can merge. That's when you say break. To me, that's talking about like separating like water or something. You know.
Well, these are like electrophilic or nucleophilic reactions. SN2 hydrolysis substitution. Are these things familiar to you?
Absolutely, but this is all basically a straw man argument to me. I'm not asking how they do or don't bond. I'm just saying how do they not rebond, or however you want to call it, when there is not a controlled structure already in place to prevent the phosphate.
But the problem is perhaps you don't need the control, because when you are asserting that it will spontaneously bond, maybe it doesn't spontaneously bond. So there is no problem here. That's the point.
Phosphate spontaneously bonds with the other things that form other things, including nucleotides, is they do bond. That's not the question. It's not how they bond. How do you keep them from creating wrong bondings? That maybe is a way to put it.
Okay, we've lost 3 viewers since we brought up phosphates.
And when I jump,
I think you're right. I think I need to create like a website to help really point out.
Oh yes, you do.
Make your drawings from your imagination. Yes,
I think I have enough to do a little comeback at you on this stuff. And I guess the problem I had is the way you introduced it and the things you said indicated that you really didn't know what you were talking about. And
I try.
Yeah, I know you try. Okay, but that's okay. You can try. But let's see what else.
We're having a conversation, not roasting anyone. So, Joel, when I joined back, and I apologize, guys, I picked up my kids and was in a bad area, lost the signal. But when I came back, you guys were talking about epigenetics, something about prokaryotes, histones.
Yeah, prokaryotes, epigenetics, and histones. He had claimed that it was like a universal code, and that the codons were universal, and
not epigenetics,
mitochondria. So I'm going to push back on that.
What did you just say, Joel? About
it's certainly not epigenetics. That is certainly not universal, but there are universal information paradigms within DNA.
The histone code is a epigenetic mechanism.
Yeah.
So when I talk about histones, from my understanding, that's what causes the chromatid structure, the spiraling, the fractal compression, decompression for DNA, versus epigenetic. Those are markers basically on top of that, from my understanding. Those are epigenetics outside genetics, quote unquote.
I could clarify this somewhat for you. Epigenetics as a principle just means above genetics or above the genome. So it is heritable traits or heritable features or patterns that aren't stored in the genetic code. That's kind of the generic principle of epigenetics. But within epigenetics, there are subcategories. DNA methylation is probably the most well-known epigenetic pathway, epigenetic mechanism. Histone epigenetics, histone codes is another subcategory of epigenetics. And then you have a third that include non-coding RNAs. And the 3 of them together, you're right, they regulate chromatin structure, but they don't do it directly or the process isn't always a direct DNA methylation to histone code. It's a very dynamic process. But you know what histones are, right?
Yeah, it's a protein. And I'm reading, I'm double checking on here. It's the one that I'm referring to is not the epigenetic histone structure. For the nucleosome core particle.
Yeah, so the histone tails, so the N-terminal polypeptide chain of part of that nucleosome core, they can become what's known as post-translationally modified. So there's a bunch of different modifications: methylation, acetylation, ubiquitinylation, phosphorylation, and effectively, if you pull up an image of the nucleosome, which is the basic functional unit of chromatin, you can see that histone core of 8 histone proteins. There's also histone H1 that serves as a linker. But the tails, histones are kind of unique in that the tails are actually soluble, and they're not disconnected from the core, but they're not part of the core's primary globular structure.
Not part of the DNA itself, right? Not part of the code, right?
Right. Well, the DNA itself is separate, though they are in contact with each other. So DNA is negatively charged. The tails of histones are enriched in basic amino acids, and because of that, they're positively charged. Histones, as a whole, are enriched in basic amino acids. So at the bottom level, you have an electromagnetic interaction between the DNA and the histone, and that's kind of the first layer of DNA protein interaction to form chromatin. But the histone tails themselves actually fold over and lie in the minor groove of the DNA strand, forming additional electrostatic. They're not true bonds; they're electrostatic interactions.
Right.
And basically, it's like a fist that holds on to a rope, and those tails can be modified. So if you add a methyl group or a phosphate group, you can change how much that tail will interact with the DNA, and it allows the nucleosome. It allows the histone core to be either removed or slid up and down the DNA. So that's some of the players.
All of that. We can summarize that by that's the compression decompression algorithm for DNA, using modern human technology terms.
Well, I would say it's analogous, but it's not exactly the same thing.
Well, of course. That's the point of. So
prokaryotes don't have histones.
Say again. I'm sorry.
Prokaryotic organisms do not have histones.
Okay. What is a
like bacteria?
Okay,
non-eukaryote.
Eukaryotes.
If I'm not mistaken, I've read a recent article that points out that some archaea have histone-like proteins.
Yeah, there's an interesting pattern, and some prokaryotes have. They're not histones. They're not true histones, but this is very new research. There are parallels between what we observe in eukaryotes and how DNA is packaged in prokaryotes. But at this point, there's no evidence that there's like a histone code for prokaryotes that I'm aware of. And this is actually my field in particular, histone epigenetics.
Okay, well, that's really cool, and I'd love to pick your brain on this. But just to clarify something, Speed, when we talk about, or when people like me talk about universal information, it's not so much just the structure, the histone, or even the epigenetic stuff. It's the universality of the DNA structures, the 64 possible codons, and how there's identical start-stop codons. There's things that are the opposite of random. That's what they mean by universal information.
Yeah, so, that's why we know that life basically had common ancestors. Or common population.
Well, yeah, it's Lamarck's theory, but that's different.
No, that's not Lamarck's theory. That's Darwin's theory. But no, a little further.
Lamarck did actually not advocate for common ancestry. He thought that each individual species originated from like a primitive organisms, and each individual species progressed from simple to complex. So basically,
that is common ancestry, and that's also what.
No. Each individual species at its own origin.
Right. That's common ancestry.
No. Individually, no common ancestry. Each like according to Lamarck at least.
There's a question of how many original ancestors there were, but that's even in the current knowledge of crap.
Lamarck said that each species had no relationship. They each originated from a simpler ancestor, but not a common ancestor.
No.
Where did you get that bullshit biography of Charles Darwin that you came up with?
But that's changing the subject. Before we move on to that, the chromatids. So how does the bacteria, the poly, whatever you call it, polycrates, whatever, how do they do their compression? Do you know?
How do they what?
How do they do their compression decompression technology if it's not through the histones? I'm curious.
What do you mean exactly by compression decompression?
Well, that's the whole purpose of the histone oxiders that we're talking about, where when the DNA coils and turns into the chromatid or chromosome, whatever you want to call it, it's archived, it's compressed, and then that's how they're able to crap so much stuff into such a small space. And then so that's the inactive.
They don't do data compression. That's not how. That's not the same. No. And
then not only is the
DNA is just coiled, not compressed like data compression.
That's what compression is. And so not only does it get compressed in the coils, but then the coils themselves matter as far as where they touch. So even inactive genes or sequences, actually the three-dimensional position matter as far as what they're doing, what the business, the coding that they're doing. But so then like you were talking about, the histones, they partially dissolve, whatever, they unravel. That's a decompression. That they move out of the range so that decompress out of the physical state, so that other things can come in and read a more or do more custom type unarchived, so to say, data transcription from unzipped or unarchived, however there's multiple ways of describing it, parts of the DNA. So I don't know enough about bacteria. I assume that the bacteria DNA is not just uncompressed. Does it have chromosomes?
So a bacteria does have a genome, but it's much smaller than the eukaryotic genome. Okay. And it is coiled and then supercoiled, but not basically at the surface level. The bacteria don't require sophisticated packaging, and the technical, it's not known as compression and decompression within the field. It's known as condensation and decondensation. Okay. Condensing and decondensing.
Yeah, that's irrelevant to me, man. I apologize. We can call it whatever you need. Go ahead.
Well, I figured you'd want to learn. But that's fine.
So like in every field of science, there's, I guess, preferred nomenclatures, but you don't have to stick to those.
Well, it's preferred that you do, because otherwise you will be talking alien to other people.
The entire reason it's preferred, though, is that if you mention a different term, even if it means potentially the same thing, you might be referring to a different discipline.
Well, and that's the thing. When you're in actual science, everything is multidisciplinary, and so we try to find what seems to be the next better nomenclature. We never keep static. Science is always changing.
What is actual science? What do you mean by actual science? When you're in actual science, what would the person's,
like I said, when you're doing something for a living, when you're getting paid to do something outside of school, for example, and you're actually doing things with other, again, not just your own multidisciplinary field, but other people doing multidisciplinary fields.
Like somebody involved in medical research, cancer biology, maybe.
Not nanotechnology, like my fields. When I started working as a nanotechnologist, I was not a plasma physicist. I had to learn to be a plasma physicist. When I started working at SpaceX, I was not necessarily a rocket scientist by trade or by education. I had to learn to become a rocket scientist.
What did you do in, what did you say, nanotechnology?
Yeah. I was doing
What kind of work did you do?
if you're familiar with micro machines, the MEMS research, as well as making R&D for chips.
For creating microchips?
Yes, and again, MEMS, micro machines, nanotechnology, nano machine, what do you even call it? Small stuff, the little gears and the little accelerometers. And
When did you work on that?
99 to 06.
Okay. That would be interesting. I'd like to see links to some of your work.
Yeah. No, they hired me as a senior. I forget what they called it. It used to be a TGCM, whatever. But I ended up basically running all of the SCADA, all the bunch of the data stream stuff. And so now they also gave me funds to make my own what's called a MFC, a mass flow control lab, to be able to better, more efficiently calibrate and get those things back in the machine. So all that required talking to all the other engineer groups. So I, basically whenever I go bring an MSc up to one of the diffusion lab groups, for example, they're asking me, okay, well, they're having these problems with their diffusion processes. So we would sit there and troubleshoot the diffusion stuff. And then when I got into plasma physics, when dealing with the dry and wet etch plasma etch machines, the same thing. I'm the guy I was the guy that was doing some of the basic, whatever you call it, for the components for the machinery. So of course I understood the functions for those components. So then naturally all of us engineers would combine our efforts and work together and try to solve these bigger than these problems that did not exist. That's what I also mean by science. We don't work on things that we already know about. We try to create the new thing, the new paradigm. We invent things that nobody thought could exist before. We invent them, and then we have to put them behind non-disclosure agreements. But regardless, I was just lucky. I was a young kid, fresh out of the military, and I was able to hobnob with all the different groups and learn all these. Same thing as SpaceX. They hired me to mostly work on big data and telecom stuff. But to do that, I had to understand all the processes for all the structure, all the rocket engines, all the different processes, all the tests we were doing. So to help them do that, help them do their job, I have to learn their jobs. It's like, Yeah.
So,
Anyway.
so Joel, are you comparing prokaryotic genomes versus eukaryotic genomes? Do you feel more comfortable with that? Like, prokaryotic genomes are much, much smaller. There still is higher ordered packaging, supercoiling, but not to the degree that we see in eukaryotic cells. Certainly there's not a well-defined histone code in bacteria.
Yeah, I would say I wouldn't care so much about the size or even the complexity of it, just that there is a compression decompression process. And that's what I'm interested in. I'm interested in the technology of DNA, of life.
Well, how do you compress a digital file?
Yeah, we talked about that on Tangelo's channel, as a matter of fact, the other night. So you're talking about the human capabilities. We have lossless versus lossless type compression ratios, and that is completely different than the way life does it. In fact, on Tangelo was sharing an article how they're measuring the compression ratio for DNA is like 7,000 times, which is just crazy. And he was asking me, what's the best for our algorithms, and 7-zip and WinRAR and these other more popular protocols. Their best rate is like 80 to 85%. Maybe.
The DNA doesn't get compressed in the same way that the data compression. No, it doesn't.
It's a lossy compression. It is, just like we do ours.
You just said that it's completely different than what we see in life.
Compression. There's compression, decompression. There's codecs, right? And then there's different, even in the human technology, there's different varieties of compression, decompression. So the way life does it is just that it's got its own level of varieties, but it's so vastly, billions of light years technologically advanced in the way. So our efforts and what guys like me are hoping to try to do is understand how life does it so that we can reverse engineer it for our own technologies and just revolutionize everything that we're doing right now.
Well, can I ask of anybody, if I understand correctly, data compression is just like when you have a file of information, like 10 kilobytes, for example. If you compress it in data compression, you can make it smaller, like in 5 kilobytes. Just an example. But DNA doesn't do that. Like you still have the same amount of DNA nucleobase pairs.
Right.
When you condense
They
it.
occupy less volume.
Yeah, they occupy less volume, but not data volume.
The amount of data
Right.
there is not compressed or decompressed. The amount of information
It's still there.
Right. Just like in lossy data compression for human technology. So DNA is not a binary code. I mean, there's not math involved necessarily. Well, maybe there is. That's part of the challenge, trying to learn it. But there's I think the human DNA, they say it's like 6 feet long or whatever. It's some of that fits into an area that's like 2 5,000ths of an inch or something crazy. So that's compression, and it's a physical code. It's not a binary.
It's compressed in a volume, but it's not like compressed into a small data amount. It's not less nucleotide base pairs.
It's still a process of compression that we would love to learn how to do.
I mean, this is the ultimate equivocation fallacy going on here, because
it's compression, decompression. It's codec technology.
It's reducing the amount of volume that the DNA takes up.
It's winding the DNA into a compactor space, but not compressing the data itself.
The actual information, like between chemical bonds, isn't being lost.
The information stays the same. It's not compressing the data.
With lossy information compression for human codecs is exactly the same. You don't lose any information. But
you're compressing the data in smaller amounts of bytes, but with DNA it doesn't happen. That doesn't happen.
I see, again, that in the scientist mind, it does happen. How do we reverse engineer it? How do we adapt it to other things?
It's just outright denial mode here. So sorry.
Let's reverse engineer. So Joel, I am a scientist. Histone epigenetics, chromatin dynamics is my specialty. Cool. You're talking about nebulous scientists out there. You know, this is literally my expertise.
Right, and we were talking about this 20 years ago when I was working on the
breakdown.
That's out there.
Say that again. I didn't hear you.
Oh, people were talking about how to reverse engineer the codec technology in DNA into our own binary technology 20 something years ago, back when I was working on this too.
Sure. Yeah, it's not new. Bio nanotechnology is a well-established field now, though it's not especially productive as of yet. Of course, bio nanotechnology argue with me about that, I'm sure.
Say you were reversing the 4-bit code for DNA.
No, well, that's another hopeful, paradigm change, but that's different than codec technology.
Yeah. Was it the 4-bit code?
Yeah, there's
4-bit.
I want to establish something clear. Like when you describe DNA as to be compressed, like for example, human DNA has about 3 billion base pairs, right? So if it gets compressed, do you believe that the amount of nucleotides goes down from 3 billion?
It's a lossy compression. If you don't understand, how lossy versus lossless codecs work in human technology, then there's no reason to try and talk about it outside.
Explain.
I'm sorry, I heard multiple people ask multiple things.
Okay. There's no reason to talk about this with molecular biologists?
Well, if you're not going to, if like Nestle, how do you pronounce your name, sir? I'm sorry, Nestle Go?
Just call me Ness.
Yes. Yeah, you're saying if you don't understand how lossy codecs work, the terminology for compression, decompression stuff, then how are we going to be able to share the theories and the ideas of how to merge this technology into other things, to make new things?
You talk about it. You explain the concepts in your relative fields.
Right.
Why don't you explain that? Like you said that a certain type of compression, decompression is more similar to what we see in chromatin. Why don't you give us a little bit more detail on that, like exactly how that's more similar than other types of compression?
Right. Now, there's a similar to chromatin. It's what's called a lossy compression decompression technique. So, like in human technology, we'll take, for example, I guess this is frustrating. I apologize. We'll take a file you know, like a picture, for example, or even a VoIP stream like what we're doing right now. There's a gigabit voice VoIP stream of our voices being shared right now. So depending on which codec protocol you want to use for TCP/IP or UDP or whatever, it will try, and there's different varieties of ratios of how it'll either compress it by losing information, the lossy compression, and I apologize, I think I've been reversing that, versus lossless codec. Lossless codecs are where you don't actually remove any information. You keep it the same amount of information, the same type, and we do different types of basically math algorithms to try to simulate what certain chains of information are to make it smaller so that you don't have to transmit the full gigabit. You can only transfer, and again, the best technology we've got right now, best math is about you can do about 200.
What gets smaller?
Pardon?
What you said, so that it gets smaller. What specifically is getting smaller?
The amount of data. So you don't transmit the full gigabit. You're only transmitting the smaller, the compressed amount of data.
And how is that analogous to chromatin condensation?
Because there's a 6-foot long piece of physical 3-dimensional bidirectional packetized codec technology, whatever you call it, in life, that's fitting into a 2,000th of an inch bubble. It's like, how the heck does that fit? It would be awesome to be able to figure out how to not only compress our own data that way, but even other physical structures. Even
but when we compress computer data, we don't compress it in a smaller physical space, like
including nano machines. Yes, we do. We would love to be able to do that kind of compression technology for nanotechnology.
But it's apples and oranges.
Yeah,
it's compression technology. It's the same thing. It's codecs.
I mean, he's equivocating on the top of a head here. Like,
no. Yes. You got data and you got physical structures.
Like, in one sense, you're compressing data into smaller, like data size, and one time you talk about physical size, like you're compressing into a smaller volume.
Right. Try to we want.
These are not the same. These are not the same.
If we translate data physically, such as through photon packets, for example, it would be awesome to be able to understand how life does it, to mimic it, to reverse engineer that.
Yeah, and I would agree in that circumstance, if data was transferred physically,
yes,
physical data, it would be more analogous. Not perfectly analogous, but more analogous than zip files or other forms of compression today. They're poorly analogous, if analogous at all.
So that's the difference of opinion, and I mean, again, I'm talking about the technology. I just want to understand the technology. That's what it is. What life does is technology.
Well, you have to do a better job, I think.
Yeah, you got to learn molecular biology for one.
Well, that's the point. So how does the histone chain, the histone structure, physically compress in the lossless compression?
I have a better analogy. Like imagine a yarn, and you're coiling it up. That's it.
It manipulates a property inherent in the inherent in DNA, and that's the fact that DNA is a polyanionic acid, so it has multiple negative charges. So when you include proteins which have positive charges next to it, the DNA will start to coil around it and reduce its volume.
That's awesome. Let's learn how to do that for other things.
Well, there's some attempts to do it with like sugars, but also to do it with DNA.
Yeah, or again with whatever else other technologies we want to do it with.
Yeah. What's the starting volume of a data packet?
Whatever.
What are the dimensions of that need to be condensed in the same way we do chromatin?
Again, it depends on what substrate we want to talk about. Are we talking about something in a nanotechnology factory, or are we talking about internet stuff? Ethernet packets. I don't know. There's a huge variety. We don't limit ourselves to one particular group or paradigm or even concept. With the technology, the ability to know how to do these things is what we want to revolutionize our current technology level with. We want to match our current technology, which is
yeah. We all agree. We all agree with multidiscipline. Relative time. Get specific. Where the issue is because you're talking about these concepts in such a general way that it's easy to construe parallels and easy to claim they're analogous. But when you get to the details, like for instance, that DNA is a physical substance that has volume, and to answer your earlier question, what is it about DNA that allows this packaging? It's because it's a unique macromolecule. It exists in both the macro scale and the nanoscale. It's nanometers wide and meters long. So you're talking about truly a very unique substance. Because it is so thin relative to its length, that is what enables this higher ordered packaging. What in data technology computation, what's analogous in that respect?
Well, again, we could probably try to think of all kinds of ideas. I mean, I'm thinking about some of the things we're trying to do for space technology, for example, to be able to compress certain things, you know, whether it be, you know, anything from just
when you say compress, you mean making things smaller.
Yes.
Well, and for instance,
So now data compression means smaller.
Yes. Always has.
Well, and I think the difference might be it's like the way DNA is storing information is due to the fact that DNA is something which is topologically unique. It's something that its four-dimensional structure can be distorted and manipulated.
Cool.
Whereas
do that, right? That's all I'm asking.
Yeah. We're supposed to, like, if I'm not like misrepresenting traditional coding, it seems like you're storing it by means in more or less a linear fashion, by storing strings of ones and zeros or hexadecimal or whatever.
That's the information side of DNA, the 4-bit, you know, the three-dimensional bidirectional 4-bit structure of it. And then there's the physical structure of it. Well, we have the same types of things we want to try to do in human technology.
This is where I run in the problem with you using the word compress, because when you compress the ones and zeros, you end up with less ones and zeros. But when you quote unquote compress DNA, you're not ending up with less A, G, and C's. It's the same amount.
It's right. It's a compression of the physical molecules.
That's what like you are. That's what I had a problem with. You are conflating compression from one thing with another thing. Which is
all right. Well, I'm a telecom guy. We've got all kinds of crazy ways we love to try to do different codecs and stuff, and that's one. It's a technology to me. So I want to see how I would love, and there's a lot of people besides me that would love to see how we could use the technology that life uses to physically and whatever archaically, however that word is, compress itself into what we use for our own technology. If we could do what DNA does, computers and the internet would be radically different today.
Okay, guys, we're up on 2 hours here. Are we getting anywhere? I don't think so.
No, I don't think so.
I doubt it.
Yeah,
well, you guys want to stick within, I guess, a strictly evolutionary type mind frame versus those of us that want to steal from evolution, so to say, or steal from how molecular biology does things, and to steal that technology, which is what it is, and to make it into adapted to other technology.
But all like computer technology also steals from evolutionary biology. Like for example, you have evolutionary algorithms, right?
No.
Yes, you have. Evolutionary algorithms are real.
I think someone mentioned that about there. Some guy named Ron, one of the other debaters on another channel, saying that AI can program itself. he's
oh no!
Major. I'm like, what?
I gotta mute for a second here.
Say again.
Speech just muting himself.
Oh. Yeah, I don't. Yeah, I mean, we got everything that I know of in code. It has a purpose. It doesn't have like and maybe that's something Speed and I could probably talk about, the ideas of self-evolutionary type code or whatever. And there's certainly ideas for it, especially in the AI world, but it's very impossible. It's annoying.
In what way?
Well, not only do you have to have self-aware, basically, type AI or very highly developed, pre-developed heuristics for it to even begin to do that, and I guess to be honest with you, I'm getting kind of.
No, and if you're getting burnt out, that's a different conversation. Yeah, I get it.
Thank you. I really appreciate that. But no, we work on things of trying to make AI adaptive, and I think I did touch about that with Tantangelo's group about spider bots and random word sets and stuff like that, dictionaries and stuff like that, trying to, and even with the like IBM Watson's attempt, for example, trying to analyze volumes of healthcare information, for example, trying to figure out new decision making skills and stuff like that. All these, it's a very difficult to basically impossible task. We're getting to the point where we're basically trying to create more automation than we are like a self-evolutionary type path.
Yeah, I mean, AI is not. I'm not a programmer of any type. My background is in biochemistry, but there seems to be like two approaches, like to training AIs.
Yeah,
and the difficulties getting those fields to merge.
I'm sorry.
No, go ahead.
No, I was actually loving the way you said that, and there's probably plenty of similarities between the molecular biology versus AI development. In fact, that's where we talked about how some of these, apparently cognizant functions within DNA do at least appear, if they're not actual AI algorithms, that we could reverse engineer. And so, the auto correction techniques, the antivirus techniques, there's all kinds of parallels that we can learn from.
You had mentioned something about that earlier. I was wanting to, can you point? I know you got into talking about transposons. Is that, what do you mean by cognizant?
Where they at least appear to have, just like cognizant AI, they appear to have a mind of their own. What Elon Musk is specifically trying to prevent.
They appear to have what?
A mind of their own, self-aware or self-thinking capabilities.
Yeah. So,
but transposons are not self-aware. So yeah.
I thought you corrected yourself earlier and said that if you were describing these things as though they had a mind of their own, that's not what you were saying.
Well, again, they seem like they do. We're trying to see if we could do that, but
what do you mean they seem? Like, what are you describing? What they seem?
There are, for example, all kinds of what they call chatbots out there. Google's making some pretty amazing ones, Apple as well. Where the whole Turing complete philosophy, for example, back from the 1940s and 50s, was that we'll have technology eventually that you cannot distinguish between a machine or a person.
I mean, like, what are you describing in the DNA that seems to have a mind of its own?
Where
he's talking about transposable elements. So,
I don't see how transposons have a mind of their own.
So it's not just the transposons. That's just one of the more glaring examples. And there's all kinds of things where there are components that are part of the DNA, but they're not DNA, that are making decisions.
Okay.
Well, they're acting upon they're acting upon chemical information already within the DNA. I mean, so things like methylation of CpG islands are doing that because of the topology around that local region.
Right. So they either float around randomly and hope to God they land on whatever chemical bond they need to be able to do something, or if they don't, then you die. Or it's and the things that I've been trying to pay attention more to is that they're not random. They're specifically designed. They grab on, they swing from one specifically designed RNA chain to another to purposefully move around certain areas to on purpose go do certain things in places.
So here you go, like you're almost constructing a false dichotomy between pure randomness and mind of its own. Like,
I mean, chemistry itself and biology, for that matter, is a stochastic process.
Well, if it's not, yeah, go ahead.
Are you saying chemistry isn't a stochastic process, or?
I have no idea what that is. I apologize.
So it's a process that's inherently probabilistic. So chemistry is founded off of quantum mechanics, and when we describe chemical reactions or chemical interactions, we describe them in a probabilistic manner. But the result of those can still be predicted to a high level of certainty.
Okay, yeah, you're talking about statistical mechanics. That's not the same conversation to me. I'm talking about the ability for things to do things outside of just a strictly, what do you call it, a non-cognizant, I guess, function.
Right. So in this case, I don't think molecules have an intention to bind with one another to facilitate some function.
Right.
So, like, from what I can deduce from what you are saying, like it's almost like you are saying that when you see something as being cognizant, you are saying it acts in a non-random fashion.
Well, yeah.
So it's so basically what you are saying is, it seems to be cognizant. What you're actually saying is it seems to be non-random. That's it.
Yeah,
That's
it's
it.
like if you see
Alright.
two people driving a car, one guy's just kind of driving.
But I don't agree with the dichotomy. I don't say it's either random or it's intelligent or it's a mind of its own. I see it as a false dichotomy.
I disagree. I like to analyze everything.
Okay, guys, can we wrap up? Maybe figure out where we want to go from here. I would like you, SFBMOD, to talk to Leo Phileas about physics and cosmology and time and relativity. So that's one conversation. So I don't want to scare you off on that.
Yeah, no, that's cool. I appreciate it. You guys.
Anyone else want a one-on-one with SFB at some point?
I can say that I've appreciated his patience. You know, it's not it.
Yes.
At many times we kind of gained on you. I apologize for that. I don't like to participate in, you know, dog fights or just drama for drama's sake.
Same.
So
no, I also agree with that.
Productive on the most part. I don't personally see any point in having. I don't have a desire for another one-on-one. Joel, if you want to talk to me about some of my, you know, some of the things I work on, I'd be happy to do that in the future.
Yes. Absolutely. Yeah. No, I'm a big Robert Heinlein fan, where he says, I never learned from a man who agrees with me. So yeah, you know, if you've got information that'll help me learn something, regardless if I agree with it or not, I would love to pick your brain. Yes, thank you.
Yep. Let's see. I think I'm good. I thought maybe I'd want to have a conversation with you about the Bible and belief and stuff like that, but I think I'll pass on that. But Leo Phileas, I think, definitely would like to talk to you. And Immutable, do you want to set up a one-on-one later?
What topic? I really don't care either way.
Okay. Well, we'll kind of leave it open. You have been very patient and polite, and you know you're in a room with 4 atheists, and I apologize for that.
No, please don't. Yeah, no, you guys are great. I mean, I was kind of concerned seeing some of the other shows you've had, but when I come to these kind of conversations, I don't care what people's religions are. I just want the information. I want the ideas.
Yeah, well, we don't allow believers on Saturday Night at the Atheist, and we don't want you guys to watch. Okay. So basically, it's a private. It's sort of like it's private for atheists. So don't let that concern you.
It's like a stress thing or something.
Unleash on you guys on that show, and we're going to unleash on you. But don't watch. Please don't watch. So
try not to.
But you know, the day shows we do. You know, we're not bad people. We like ideas and we like to talk. And you have you told us you're a plasma physicist, a microchip designer, an information scientist, a programmer. You launch rockets, and you're an inorganic chemist. So I guess we had to look into what you said about phosphate chemistry. So, and I will look at
not all that all at the same time. It's just stuff I've done over the years.
Okay. I'm just, reading your resume. Okay. So I think we're good tonight, guys. So let's end the broadcast. You want to do that? Right. Okay. Good enough. Yep. We are ending, guys. Everybody in the chat, thank you for showing up. I think we had like 16 people at one time, which is a record for this fucking little channel. So goodbye, guys.
You have a great night. Thank you.